Okay, this is our last video for our Type 4 review, and it's going to be dealing with graphs again. So this was a quiz, so please make sure that you did this problem before we move forward. And if you have, let's go ahead and get started. We're given the graph of g, and it says the graph of the continuous function g, the derivative of the function of f, is shown above or below. The function g is piecewise linear for the interval -5 to 3, and then it gives us an equation for g for the interval from 3 to 6. So you can see that it's linear all the way through here, all different pieces, but then it turns into a parabola on this side, and that's going to come into play later on. So here it says, if f of 1 equals 3, what is the value of f of -5? Well, because I wasn't given anything specific in this graph about f, I've got to do a translation here. And that comes from this statement here. It says that g is the derivative of f. So I'm going to write that down. G is the derivative of f, or g of x equals f prime of x. Now in part A, it says that what is f of -5? Well, how do I get to the value of f when I'm given the f prime graph? Well, remember the value of a function is equal to the initial condition, and in this case the initial condition is 3, plus the integral from the x value of the initial condition to the x value that we want of f prime of x. So we can say f of -5 is equal to 3 plus the integral from 1 to -5 of f prime of x dx. And because f prime of x is equal to g, then all I have to do is find the area. Let me take a step back here. All I have to do is find the area under g, because I'd be looking for the area under f prime the same way. Now one thing I note here is that this is an integral from 1 to -5, so we're actually moving backwards. So what I'm going to do is I'm going to flip this integral so that it says 3 minus the integral from -5 to 1. That way I'm just moving forward, it makes it a little bit easier, of f prime of x, or in this case g of x dx. And so we have to find the integral from -5 to 1. Well, to do that, we need to break this into pieces. So the first piece I notice is the trapezoid here. So we can see that this trapezoid has a base of 4, it looks like, and another base of 3, so that's why we have 3 plus 4, and then it has a height of 3. And so that's the area of that trapezoid. And notice that that height is a -3 because it's below the curve. Now from there, we would find the area from -1 to 0. Well, that's just 0 because that's just a solid constant line at 0. And then we have to find the area from 0 to 1, and that's just a triangle. So that would be 1/2 of 1 times 2. And then when we go to simplify all that, we get 3 minus the quantity -21 over 2 plus 1, which simplifies to 25 over 2. And again, that's because we're including that 3 minus that initial condition at the beginning. Alright, the points on this, you would get 1 point for having the correct integral. So basically, if you had this written out, you would get the 1 point, and then you're going to get 1 point for your answer. For part B, it says evaluate the integral from 1 to 6 of g of x dx. Well, that's pretty straightforward, it sounds like. We're looking for the integral from 1 to 6. But notice what I have here. From 1 to 3, I have a nice constant function. That's just a little square. But then the integral from 3 to 6, that's a parabola. And I don't know the specific equation for finding the area under the parabola. So what I'm going to do is I'm going to break this integral into two parts. I'm going to break it to say the integral from 1 to 3 of g of x dx plus the integral from 3 to 6 of g of x dx. The first part's easy. The first part is just 2 times 2. That's the integral from 1 to 3. The second part, when I'm saying the integral from 3 to 6, well, I don't know how to find that area graphically. But because it gave us the function g of x for that interval, I'm just going to replace g of x with this, the 2 times x minus 4 squared, in place of g of x here. Now, in my case, I expanded that all out. I multiplied that out. I said x minus 4 times x minus 4, and then I distribute everything and combine like terms. So I got this 2x squared minus 16x plus 32. Now, I don't know why I did that directly, but we'll talk more about that in a minute. Going to simplify all this, well, 2 times 2 is 4. That's easy. To evaluate this guy, we have to take the antiderivative. So that would be 2/3 x to the third minus 8x squared, and then plus 32x. And then we have to evaluate that part from 6 to 3. So we're going to plug in 6 for that, we're going to plug in 3 for that, and then we're going to subtract those values. And then we're going to do all the work, and we're going to simplify that. And that simplifies pretty nicely to, I believe it's 10, if I remember right. Yes, okay. So the answer here is 10. Your point value here, you're going to get 1 point for the sum of the integrals. In other words, showing that you understood that the integral from 1 to 6 had to be broken up to be the integral from 1 to 3 plus integral from 3 to 6. Then you're going to get 1 point for taking your antiderivative correctly. So basically 1 point for this line right here, and then 1 point for your final answer. Now, going back to what I did here, I expanded all this out and put that in my integrand. You didn't have to do that. This was actually a pretty easy antiderivative to do. The antiderivative of this would have just been 2 over 3 times x minus 4 to the third. And then plugging in the values 3 to 6 would have been a lot easier that way. So if you did it that way, that's perfectly fine. That's the simpler way of doing it. I just started working, and that's what I came up with when I did it. All right, for part C, it says for -5 to 6, on what open interval, if any, is the graph of f both increasing and concave down? Well, we know that f is increasing when f prime is positive. And so we're going to write that down. We're going to justify it there. So f is increasing when f prime, which remember is equal to g of x, is positive. And then we know that f is concave up when f double prime, which equals g prime, is positive. Now, in terms of justification, we always want to revert our justification back to the thing that was given. So since I was given g, this justification isn't going to cut it. So we have to translate this statement that g prime is positive into something about g. So that's where our chart comes in. G prime is positive when g is increasing. So we can say, or when f prime of x, which equals g, is increasing. So really what we're looking for here is we're looking for when f prime, which equals g, is both positive and increasing. So we can see that it's positive all the way throughout this interval, but we're looking for the part that's positive and increasing. So we'd say from 0 to 1 and from 4 to 6. Now for us, it's nice because they said over what open intervals, so we don't want to include the equal signs there. Now we knew it was going to be open because when we're talking about an increasing function, that would be over a closed interval. But when we're talking about concave up and concave down parts of a function, that's over an open interval. So when I'm putting them together, it's going to be the more restrictive one, so it's going to be an open interval. But regardless, you're going to get 1 point for your answer and then 1 point for your justification. So if you don't have both of the intervals, you're not getting your answer point, but you could still get the justification point as long as this is all correct. All right. For part D, it says find the x-coordinate for each point of inflection of f. Well, going back to our chart, we know that f has a point of inflection when f double prime changes signs. Well, we don't have the information on f, we only have the information on g. So we're gonna translate that according to g. So f has a point of inflection when f double prime, which equals g prime, changes signs. Because we want to write it in terms of g, we're going to change that to say, therefore, f has a point of inflection when f prime, which equals g, changes direction. Now, in this case, we only see one change in direction, and that's when x equals 4. I know that there might be some confusion on this particular problem because, well, are we changing direction here? No, we're not, because we had a horizontal line. We weren't decreasing and then we went to increasing. Same thing in this interval. Now here is an interesting argument. We were increasing up to 1 and then we started decreasing at 3. So some people might say, well, there's kind of a point inflection somewhere in that interval. Not necessarily. We just have a constant function here, and therefore there is no concavity. It's just going to be a linear function. So it's not going to be a point of inflection if the concavity isn't changing, because the concavity is 0, I guess you could say. So we only have one change in direction, and that's when x equals 4. So we're going to say that there's a point of inflection when x equals 4, since f prime, which equals g, changes direction from decreasing to increasing. Now, as far as points go, you're going to get 1 point for your answer, and then 1 point for your justification. And please make sure that your justification is in respect to g. All right? All right, that wraps up the questions dealing with graphs. That was number 3 from 2018. Please grade yourself on this honestly and accurately, and then you're going to input your answers or your score into Socrative for the last 2 FRQs. And then our next group of problems that we're going to focus in on are rate in, rate out problems. So I will see you all later.